Welcome to The Explainer. Today, we're throwing on our digital detective hats to tackle a massive, honestly mind-bending paradox that spans the entire continuum of computation. We're going to explore a really fascinating dichotomy, the infinite, incredibly computationally heavy methods the universe uses to hide information versus the engineered, mathematically perfect systems we use to lock down truth right here on our own desks. So, to get us started, I want you to genuinely ponder this really provocative question. What is the hardest possible calculation in the universe? And we aren't just talking about, training a massive AI model or rendering some insanely complex video game. We are talking about the extreme upper bounds of, actually, scratch that, we're talking about the absolute limits of physical and quantum computation itself. If you wanted to extract a hidden secret directly from the fabric of spacetime, how much computational energy would it actually cost you? Okay, let's dive into this because the answer reveals a stark, almost unbelievable contrast in scale between two vastly different realities. On one hand, out in the massive scale of the cosmos, we have holographic spacetime. It relies on infinite, lossy complexity and these massive computational bottlenecks to practically censor information. But then, contrast that with the microscopic scale right on our local desks, digital architecture. Specifically, single-entry bookkeeping. This achieves flawless mathematical perfection and immediate proof of state.
Here is our roadmap for today. First, we'll cover the limits of computation. Second, inside the Python's lunch. Third, the FPU wood chipper effect. Fourth, determinism at index 0. And finally, we'll wrap up with the architecture of trust. Don't worry, the huge physics concepts early on are going to perfectly dovetail into practical software engineering.
All right, Section 1, the limits of computation. So in holographic theories of the universe, information is the fundamental building block of reality. But just because information exists out there in the bulk of spacetime doesn't mean you can easily access it. The ultimate hard problem of the cosmos is defined by something known in physics as the Python's lunch conjecture. This describes a specific region in holographic spacetime where retrieving information from past a certain surface requires an exponentially massive amount of computational complexity. The universe essentially acts as if it's cryptographically censoring this info. If a secret gets dropped deep inside this region, reconstructing it is so intensely resource-heavy that it's mathematically prohibited, or what physicists call non-perturbatively suppressed. It is literally the universe's ultimate vault. Which brings us to Section 2, inside the Python's lunch. And this brilliantly illustrates what we're talking about. Let's actually step inside this cosmic vault and see how the geometry of spacetime actively prevents us from decoding its secrets. Look at this spatial slice of a Python's lunch geometry. You have a boundary region, right? But as you move into the bulk of the spacetime, the wedge suddenly narrows at a minimal surface, called the appetizer, that's the dashed blue line. Then it expands again into this massive bulge, the dashed red line. It literally looks like a snake that just swallowed a massive meal. The region between the outer boundary surface and that appetizer surface is the lunch, and trying to pull data out of that bulge is where the computational math just becomes overwhelmingly complex. Now we can directly connect that geometry to the underlying tensor network model. In this network, you see projective operations happening exactly where the space-time wedge narrows. These projections create a massive, massive computational bottleneck for any information retrieval. If you drop a quantum secret into this network, the success probability of learning that information with low-complexity operations is incredibly small. The network forces you to overcome those projections, which requires immense computational power. To put a precise number on this insane burden, researchers use this exponential complexity formula. You definitely don't need to memorize the constants, but just notice that the area difference, the delta A_PL, is driving an exponential function. That represents the geometric area difference between that massive bulge surface and the narrow appetizer surface. Because this complexity scales exponentially, the universe is naturally computationally suppressing causality violations. It is a mathematically perfect defense mechanism against paradoxes. But hey, let's pivot from the vastness of the holographic cosmos down to the silicon sitting right on our desks, because we actually have our own localized version of this computational chaos. Section 3, the FPU wood chipper act. Now, what's really interesting about this slide is how the floating point unit, or FPU, which is the hardware inside your computer responsible for fast math, kind of acts like a gambler. When dealing with heavy math, it frantically throws darts using completely secret corporate seed tables burned right into the silicon, just guessing the answer. The source material compares the FPU to a giant blender. You know exactly what data you tossed in, sure, but because the math was just a probabilistic guess, you absolutely cannot reverse engineer that digital smoothie back into the exact fruits it came from. It permanently destroys the original data provenance. And this destructive guessing, it leads to what researchers call non-deterministic drift. To process information so fast, the FPU constantly drops tiny fractions in a standard known as the 23rd bit chop. It essentially squeezes continuous numbers into fixed bits. This microscopic rounding error creates a snowballing distortion over time. The exact mathematical path back to your source data, your chain of title, is permanently lost. Think about it. If the universe uses exponential complexity to safely hide truth, our current legacy hardware uses messy complexity to accidentally destroy it. Moving to Section 4, Determinism at Index 0. Look, we absolutely have to reject this lossy guessing if we want any kind of verifiable digital trust. The engineered solution, the antidote to this chaos, is the ERC 7827 standard, which utilizes a LIFO-JSON state tree. LIFO simply stands for last in, first out. It's a mathematically pure root-to-leaf architecture that strictly pivots away from the bloated first in, first out event-driven structures of the past. Because the very last item to go in is always the first item to come out, a machine only ever needs to query the very top of the stock, index 0, to get an immediate, flawless mathematical proof of the system's truth. Let's move to and see how this builds. At the core of this LIFO ledger is the syn-kernel function, which evaluates the thesis, antithesis, and synthesis. Imagine a strict, highly efficient bouncer at an incredibly busy club. This bouncer does not care about the whole line around the block. They only look at the ID of the person standing directly in front of them at index 0. First, the bouncer sequentially checks if the space is empty. Second, if it is, it synthesizes the new data directly into that open slot. But step 3 is the absolute kicker. If data already exists, the bouncer firmly and violently rejects the input. No entry. This completely prevents accidental overwrites and guarantees flawless single-entry bookkeeping. Finally, Section 5, the architecture of trust. So to actually pull this off in the real world, we have to shift our math away from that FPU gambler and hand it over to the exact ALU, the arithmetic logic unit. The ALU is like a surveyor with a precision laser. 1 + 1 is exactly 2 every single time on every CPU on Earth. By combining the ALU with these LIFO ledgers, we achieve massive breakthroughs. We completely avoid the 50% critical noise threshold where data just becomes statistically useless. We restore Noether's theorem of reversibility, which is the mathematical symmetry that allows us to trace every decision forensically. We eliminate non-deterministic drift. And, absolutely crucial for businesses, it completely erases the mask rendering costs associated with hiring endless third-party auditors just to prove who owns what. So the crucial point is how these two extremes of computation fundamentally differ. When we compare them directly side by side, the contrast is staggering. The Python's lunch in the holographic cosmos relies on exponential complexity and cryptographic censorship. It's an environment where retrieving state is practically impossible. But on our local edge hardware, the LIFO-JSON state tree gives us immediate, order 1 complexity. We literally move from a domain of impossible cosmic guesswork to a domain of precise bit-perfect truth, securely anchored right there at index 0. We have journeyed all the way from the extreme limits of computational complexity in black hole interiors, right down to the exact silicon architecture needed to guarantee undeniable, verifiable digital trust. The universe might hide its secrets behind the massive exponential walls of the Python's lunch, but here at the edge of the network, we finally possess a frictionless environment of bit-perfect truth. So I'll leave you with this final provocative thought. Now that we have rejected the gambler and possess pure deterministic truth, what are you going to build with it? Thank you so much for joining me on this explainer. Keep questioning the systems you rely on, keep exploring, and I'll catch you next time.